Hello everyone. You have been studying about the currents and the voltages in the circuits. But have you ever wondered how do we measure this current and the voltage? The answer lies here in moving coil galvanometer. We are going to study about this device first, and then after I'll let you know how to convert this into voltmeter and ammeter. So moving coil galvanometer is an instrument which detects current, right? So it detects So galvanometer detects current. Now what is the construction? Now the construction is based on the principle of moving coil galvanometer. What does this principle say? It says that a current carrying coil, when placed in uniform external magnetic field, it experiences torque, right? And due to torque, it rotates. So the construction is based on this, but first I'll write the principle. Sorry. Right? So for this, we want it to experience the maximum torque. So for maximum torque, we know the formula for torque. Torque formula is NIAB sine theta, where theta is the angle between the magnetic field and the magnetic moment, or you can say the area vector. This is also called as MB sine theta, where theta is angle between magnetic field and magnetic moment. And this angle is 90 degree. Then torque is maximum. For this torque to be maximum, first thing is we are using here cylindrical magnets. Cylindrical magnets means we know that if we have simple bar magnet, it will have a flat surface. Now for cylindrical magnet, we cut a curved part out of it, so such that this part, this end looks like this, and the other magnet is having this end like this, so that this part is curved. So what makes this field radial? These cylindrical magnets. Moreover, we have a cylindrical core on which this coil is given windings, right? So if this is your cylindrical core on which you are giving windings of this coil, right? And then the top view of the coil and the cylindrical core will look like this. And if we have top view will look like this, and if we have cylindrical magnets around it like this, so its top view will look like this. The cylindrical magnet on this side will be like this, and this side will be like this. So I am showing here the top view, right? So here this is a cylindrical soft iron core on which the winding of this wire is there, right? So this is the soft iron cylindrical core on which the windings are given, which will look like this from top view, right? And at every point the magnetic field will be perpendicular to the magnetic moment. Magnetic moment is normal to the plane of the coil. So if I draw this magnetic field line in this orientation, so this will be perpendicular to the magnetic moment, and for every orientation of the coil there will be some magnetic field which will be perpendicular to the magnetic moment of the coil. Right? Now here this is attached with a spring which is connected to a pointer, which will point on a scale which will give us the current in the circuit. So we have a pointer somewhere which is attached to the spring. This pointer gives the value of the current. So this is your scale. This is the pointer. This is the spring. This is the coil. This is cylindrical, soft iron core, and these are the cylindrical magnets. As I told you how it looks from the top, I have drawn the top view of the setup. So these magnets are also cylindrical. Now principle I have already written, that a current carrying coil experiences torque in external magnetic field which is uniform over here. Now torque it will experience will be maximum. Construction I have already explained. We can write down a few points about the construction. So one thing is cylindrical, soft iron core. Now what does it do? Soft iron core it has two functions, okay? One is it makes the field radial, for maximum torque, and torque will be maximum when B is perpendicular to the magnetic moment, right? Second point, what is the function of this soft iron core? It increases the intensity of magnetic field, which is denoted by B, that is right. And then we have cylindrical magnets. Again the function of cylindrical magnets is to make the field radial. right? Now we come to the working. We know that it is experiencing torque. Now when it is experiencing torque, this is attached to the spring. So the restoring torque, this is free to rotate. The coil is free to rotate due to this spring. Now when there is a deflecting torque due to the axial magnetic field, there will be some restoring torque, or you can say the counter torque, which will try to bring it towards its original position, right? So when this counter torque, or you can say the restoring torque, is equal to the deflecting torque, then it remains stable at a position depending on the current flowing in the coil. So you can say that counter torque word I am using, is equal to the deflecting torque, right? Now this is about the working. Now what is this deflecting torque? Deflecting torque is the torque due to magnetic field, and this is due to spring, right? What is the formula for this counter torque? This is K into deflection. This is deflecting torque. Deflecting torque, as I just told you, that this is N I A B, because this is the torque due to the magnetic field, which is maximum due to the radial magnetic field. So this will be NIAB, and this K is called as torsional constant of spring, right? And this is deflection per unit deflection. This is and this is also called, because we know that this is deflecting, this is counter torque. So K phi is counter torque. So this can also be called as counter torque per unit deflection. This is also called, this is called as torsional constant of a spring. So from this expression we can write down this I is equal to K upon NAB into phi. So from here you can see that I is proportional to deflection. So the deflection of the coil is directly proportional to the current flowing there, right? So that's why it helps us in measuring the current, or you can say detecting the current. More is the deflection, more is the current flowing there, right? And this K upon NAB, what is this? B is magnetic field, N is number of turns, A is the area of cross section of the coil, K is the torsional constant of the spring. This is constant for a given galvanometer. That's why I is proportional to phi. Now from here we can define two very important quantities. One is the voltage sensitivity and the other is current sensitivity. So we can start from here itself. This is deflection per unit current. for a galvanometer. So we can write down this from this expression, or here we can just mention deflection torque is equal to NIAB sin 90 is equal to NIAB, that is maximum torque, as I have mentioned here, right? So this will be for theta 90, this will be NIAB. Now current sensitivity is deflection per unit current. So from 2, what will be the current sensitivity value? Deflection per unit current means phi upon I is equal to NAB upon K. This is also called as current sensitivity, denoted by CS also. Now when we talk about changing the current sensitivity, it can be changed by changing number of turns, area of cross section of the coil, changing the magnetic field, or the torsional constant, which depends on the material of the spring, right? Then we have voltage sensitivity. For that we need to rub the board first. Now we can write the voltage sensitivity. This is deflection per unit voltage. Right? So that means deflection per unit voltage can be written as this, and this can also be written as this is voltage sensitivity, and AB upon K. This can be written IR, this is I. So I can be cancelled. So this is NAB upon KR. This can be considered third equation, right? Now a very interesting point here is changing current sensitivity may not necessarily change the voltage sensitivity. How? That is a board question. Now how? So you look at the formula for the current sensitivity. We know the formula for the current sensitivity is NAB upon K, right? So this is NAB upon K. So suppose if N dash is made 2 times, right? So what will happen? Current sensitivity nu will be N dash, area same, magnetic field same, K is same. So this will be 2 times NAB upon K, that makes it 2 times of the initial current sensitivity, right? But what happens to voltage sensitivity by doing this? Voltage sensitivity formula is NAB upon K into R, right? So if N becomes N dash, which is 2 times of N, then the new resistance will also become 2 times, because length doubles and R dash is proportional to L dash, right? So resistance will also become 2 times. So this will be Vs dash will be N dash, A is same, B is same, K is same, but R dash is different. So this can be written 2N A B upon K, 2 times of R, right? So this will be cancelled, and this is same as the original voltage sensitivity. So therefore there is no change in voltage sensitivity if we change the current sensitivity by changing the number of turns, right? So this is very interesting. So this was all about the basic concept of moving coil galvanometer. In the next video, we will study about the conversion of moving coil galvanometer into ammeter and voltmeter. So that's all for now. Have a nice day.